class loaders. Let me go full screen. Okay, there we go. So if anyone does have any questions, please do wave at the camera. I can see you all. So yeah, do wave at the camera, and we can take questions and discussion as we go. So, do you really get class loaders? My name's Simon Maple. Thank you very much for the introduction, Con. If you wanted to follow me on Twitter or tweet me, in fact, because I've got my Twitter stream open right now, so I will see your tweets live. And if you did want to ask questions on Twitter, please do so as well, and I can catch your tweets if you at me. So at SJ Maple if you wanted to tweet me. So let's dive straight in. A little bit of background as to why we're giving this talk then. So as I work for ZeroTurnaround, people probably recognize ZeroTurnaround from the product we have, which is JRebel. And JRebel is a product which works at the class loader level. And we've had to do a lot of hacking on class loaders, or existing class loaders, to understand how we can reload existing classes. So we don't create new class loaders when we do this. We actually hack into existing class loaders. We can do this with regular Java SE, but the complexity really comes when we look at containers, whether that's Java EE or a simple Tomcat or Jetty container. There are a vast number of containers that exist a vast number of class loaders that exist in containers. So it's very, very important we understand how we can integrate with them. And I'll talk about how you can integrate with class loaders a little bit later. But first, I want to talk about what we're actually going to cover. We're going to talk about what class loaders is, what class loaders do, how you can access class loaders explicitly, or how you can load classes implicitly, some of the problems that you'll have no doubt experienced when using class loaders, and one of the problems with leaky class loaders. So you've heard about how you can leak a class. What about leaking a class loader? What are the implications and so forth? So to start off with the basics of class loading, who's actually used, let's do a show of hands, who has used the class loader API directly?
That's a no.
So no one has grabbed the class loader API directly. That's actually a good thing, because typically, you don't need to use the class loader API. It's something that you only do when you need to. You must have a requirement that you need to do something like this. Normally, if you just reference a class or use a class from within your Java code, the JVM will automatically load that class for you. But this is the class loader which is being used under the covers, and there are many different implementations of a class loader. So, for example, Con said, I used to be a WebSphere application server developer, and it's nice not to be in a room when everyone's groaning when someone says that. But how many people are using WebSphere app server right now?
Got a couple.
A couple, okay. So how many class loaders do you believe exist in WebSphere application server?
Too many is one of the answers.
Too many. That's actually accurate. Yeah, we have. I believe. Let me think. I think it was about 350 class loaders or something around that kind of figure. Which you'd think, well, why are there so many class loaders? Surely class loading can't be that difficult. But they all do very subtly different things. But this is the kind of base class, and there are a number of methods on here which typically tend to get used very, very commonly. Let me show you them. Let me grab a highlighter. So load class is the most important method. This is the class which everyone will call. If you're going to use a class loader, this is the method you use. And typically you pass in a string, which is your package name and your class name, and you will get an instance of a class back. And this is going to be a class which the class loader has found on its class path, and it will provide it to you so that you can instantiate an object from that. So fairly straightforward. Define class does a similar thing, except it grabs a byte array and will create a class from that byte array. So you actually pass in the class itself as a byte array. Quite subtly different. Whereas with the load class, the class loader has to actually find the class itself. Now you've got a couple of get resources methods, and these are very, very key to try to diagnose a problem with a class loader, because they provide a URL or an enumeration of URLs back when you provide a string of a class name and a package name. So basically, I say, this is my identity of a class. Provide me with a location where you have found that class on your class path. It's very, very good for removing your assumptions of where you think the class loader is getting a class from and understanding exactly what the class loader is doing. The final method on this class is getParent, and this is a key method in trying to understand the hierarchy of a class loader structure, because a class loader isn't a flat structure. You have parents, and parents have children, and you essentially go up and down this structure, delegating who should look for a class and who should load a class. And this is key to the problems which we're going to see a little bit later. So let's start at our base example. Hopefully my audio and the slides are in sync. I don't think they'll ever get out of sync, but hopefully that is the case. So let's start with example 0. We have a class A, and we have a method, do something. That do something method instantiates a new class B and calls do something else of that class B, of the object B. So a quick question then for the audience. Which class loader is the class loader that loads class B?
The same one that was used to load class A?
That's exactly right. It's all about scope class loading. So essentially, the class B could be essentially loaded by whichever class loader the declaration of B exists in. So here the declaration exists in the scope of class A. As a result, a similar code to this is going to be called. We effectively get the class loader which loaded class A, and we use that to load the class with class B. It's a key part here to notice that every single class does have a link back to its class loader. So every class has a link to the class loader which loaded it. Okay, now let's look at something a little bit more complex. If we ignore just for the moment that we have wall1 and app1 in these boxes, we can see that if each of these boxes were a class loader, we can see the hierarchy where every class loader typically has a parent up until the very, very top class loader, which will be the system class loader. And we would also notice that, you know, let's say we're in this bottom left box. What we would expect from a class loader is that when we call load class, rather than that bottom left box try, in fact, let me see if I can, there we go. Rather than this box try and load the class itself, it will actually delegate to the parent first, this the box noted by app1.ear. This class loader would then delegate up to what would be the system class loader, and this would try and load the class. Because there are no parents, if this system class loader could not load the class, it then delegates down to say, can my child load the class? And it's very important that this system is adhered to, so that we have the very top level class loader trying to load the classes first and then delegating down to the leaves. And this would work perfectly, except we don't live in an ideal world. So what happens when we actually introduce containers is we have our container class loader at the top, which is effectively something which you would expect if this was, say, Tomcat, to load our lib directory jars and you know, that kind of thing. We would then have, if we had an application sitting on that, we would have an enterprise archive style web class loader, so an application class loader. Then if we had a number of web archives inside that ear, we would individually, for each wall, we would have a web class loader. So here we're starting to see our structure. And what we would expect to see is our web class loader to delegate up to our application class loader, and our application class loader to delegate up to our system class loader, or our container class loader. And that would be beautiful if it all did that. However, there are instances where we don't want it to do that, because let's say our container, let's say it's WebSphere, uses a specific log4j or a specific logging system, and we don't want our application to use the same logging environment as our container. What we can do is we can set our container up so that our web class loader delegates to local first. And what this means is it will always try and load the class itself before delegating up to its parent. So our order, if that was the case, would be, first of all, we're going to start with the web class loader. It tries to load a class itself. Only if it cannot load the class itself on its own class path does it then delegate up to our application class loader. If our application class, our application class loader would then behave as you would expect and delegate first before trying to load the class. So it delegates up to the container class loader, and the container class loader tries to load the class. Only if it fails will it go back to the application class loader, and it will try and perform the load class. If it can't then load the class, you will get your usual no class def found, and you'll get the exception, which we all come to know and love. And it's this difference with the web class loader which causes many exceptions and problems, which we're going to see going forward. Any questions on that before we carry on?
All good so far?
Okay. One thing I will mention before we go on actually is the strategy for every application server or every class loader can be different. So for example, WebSphere app server, WebSphere will actually, let me think, what does WebSphere do? WebSphere will always prefer parent first. So in the WebSphere case, we will actually start at the container class loader, the shared class loader, then we'll go to the application class loader, then we'll go to the web class loader. You can set on the web container a setting, a flag, that will automatically make the web class loader search local class path first. And that's when you want to override some of the logging settings or whatever. Tomcat, on the other hand, will always check local first. So we'll always check the web class loader before going up to the shared class loader. So it's interesting to see, depending on which container you're using or which app server you're using, it's important you know and understand what your default is so that you can understand how your application is behaving. Okay, so yes.
Sorry, Simon. Quick question then. So is there a way to see what the strategy is for the class loader hierarchy if you've got a container that you've never seen before?
Yeah, that's a great question. Yeah, so the best way of actually doing this is to use our good friend Google, because very often containers will use convention over configuration, so you won't necessarily see the default that the container is using. So the best way to do it is literally to Google through your container docs and work out what the default is from there. The alternative is you can of course just test it. If you had a class on your shared container and a class on your shared shared directory and a class on your webinf classes or webinf lib with the same name, and you try to load it, you can see which class it would get first. So there's a couple of ways of doing it, but the docs should be clear about which strategy it has.
Cool.
Okay.
Yeah, sorry, I got one more question.
If you were using WebSphere, you can go into the web admin console, and there's a section in the performance tab somewhere where it lays out how the class is loaded and where the class loaded.
Cool. All right. So I don't know if you heard that, Simon, but we just had a member of the audience talk about that there's a admin console in WebSphere, which you probably already know about, that shows you the order of class loading.
So yeah, WebSphere is a little bit easier because of the web console, the admin console. It pretty much it's kind of its own friend and its own worst enemy in that it does have every single setting you could possibly set on its admin console, which is great because you can see the behavior. But it's its own enemy because it's got every single setting you can imagine in the admin console. So it's hard to find things sometimes. But yeah, if you go to I think it's under servers, and then I think web container or something like that, then there is a setting under WebSphere specifically. With things like Tomcat, you're obviously it's much harder to find because there's very minimal web container admin console and stuff like that. But yeah, great comment. Okay, so let's move on to problems then. So I'm going to jump into Eclipse. What I've got in Eclipse here is just a managed Tomcat server in Eclipse, and I've added this this CL demo. And this CL demo, I've got a bunch of servlets. Hopefully you can see this. How does that look? Does that look good?
Good.
Yeah.
That's good. Awesome. So here we have a test1 servlet. And what this test1 servlet is going to do is it's going to, on do get, we're going to grab util1. We're going to say hello on util1. If I click on util1, you can see say hello is there, and it simply returns a string hello. And all we do is we system out, we print that out, so we'll be able to see that on a web browser. So let me go to HTTP. I've just got a new Microsoft keyboard and I'm not used to it right now. Localhost test1. So if we run this, we get an exception, and we get no class def found error util1. So hands up if you have never seen an exception like this before, and I don't expect anyone to put their hand up. Excellent. Oh, I thought that was a hand up, but it was a head scratch from someone in the front row. But I'll pass that. Okay, so no class def found error. I'm not gonna embarrass everyone by asking what this is. It's obviously that no class loaders in the entire hierarchy can find this class, an instance or any kind of definition of this class with the combination of package and class name in its class path. Now, one of the things that we want to do when we find class loader problems are a pain in the ass, because what we expect the class loader to be doing is rarely what the class loader is actually doing. Class loaders are funny beasts, and we need to actually remove our assumptions to really understand what class loaders are doing, because assumptions are the biggest problem when debugging class loader problems. So what we're going to do is I'm going to go back to this code, and hopefully we've got JRebel enabled so I don't have to restart this constantly. I think I have. I'm going to comment that out, and I'm going to do something which is a little bit debug on this class. And I'm going to grab, first of all, the class loader which is trying to load util1 is the class loader that loaded test1. So what I'm going to do is I'm going to grab test1. I'm going to make this bigger. I'm going to grab test1. I'm going to grab the class loader, and I'm going to cast that to a URL class loader, which is a very important class loader, a very useful class loader, which virtually all containers provide. And it's a class loader that I'm able to invoke the method getURLs on. And getURLs will provide me with a full list of locations which the current class loader can search for on its class path. So it's essentially printing me out the class path. So if I save this and run this now, there we go. So now we have, this is essentially my class path. I can see in this, what's this? This is, okay, so this is the webinf classes directory. We also have a jar in my webinf classes jar. In fact, what I could do if I wanted to is I could copy this. In fact, let's just go copy. Let's grab one of these. I'm going to cd into that directory. We can see this jar on the class path. If I wanted to, I could jar minus tbf cldemo.jar, and we can see indeed that is where I expected it. It's obviously some kind of repackaging problem. Obviously, we wouldn't do this for every class def found, no class def found error, because we'd be there all day. But this is a very interesting way where we can genuinely see what the class loader is doing and what the potential problem is. So that was test one. Let's actually look at a more interesting and more complex problem and look at test two. Okay, so test two, we're using util2, and I did notice that util2.class does exist in my runtime. So util2 will exist, and we have say hello, which is written there. Say hello returns a string. So this one's obviously going to work because it exists. I'm going to go to my runtime, and I'm going to do a test hello2. We get an exception. What is this exception? This exception is a no such method error. util2.sayHello, taking a string, returning a string, as its return value. This method does exist. So why am I getting no such method error?
It's going to return an array.
Say that again, sir.
Is it meant to return an array?
No, the method is just returning a string here in this case.
The old class?
No.
Not recompiled after
Right, now we're talking. So basically, what could potentially happen here is we have two environments here. We have our source environment, we have our runtime environment. Two very, very different beasts. Our source environment, could well compile, but our runtime environment, if that doesn't get the new version of the class, and it could be a number of reasons why it doesn't get the new version of the class, we're potentially running new code against old. So if we have the new version of our test2, which actually does invoke say hello, and this compiles because we can compile against util2, but our util2 is actually still old and doesn't have this method. We're potentially using a stale version of our class in our runtime. So as a result, our runtime is stating, I'm actually trying to call this method, but this method doesn't exist in my runtime class. And this can happen because of a number of reasons. Perhaps we've packaged incorrectly, and while we have compiled our entire project, we haven't packaged the latest versions and added that to our runtime environment. Another more common potentially reason is that we have multiple versions of util2 on our runtime, and the version which we have compiled, exported, packaged, and put onto our runtime is actually later on the class path than our updated version. And when we have two versions on the class path, Java is actually pretty stupid when it comes to this. It will always go for the first one it finds in the class path. It goes through every single directory, every single location on its class path in turn, and it will pick the very first one it can find. And if that's the older, staler version which you compiled previously, that is the version it will always use. So, and I've done this many, many times when I was working as a developer, in that I would continually repackage, rebuild, redeploy, and I'd still get the same problem. And no matter how much coffee I drank, this problem wouldn't go away. What I actually used to do as a bit of a cowboy move is I used to sometimes name my jar file with an underscore, so that if the same class did exist in the same directory, it would be picked up first by name in the class path. But I'm sure you guys are all such good developers. I'm sure you wouldn't be such a cowboy developer like myself, so that's no problem. Okay, so how can we? This is just our assumption, and I want to try and get through that. We don't want to run off assumptions here. So how can we decide? How can we work out what the problem is? So what I'm going to do now is I'm going to comment that out, and I'm going to uncomment this. So now what we're going to do, util2. We know util2 is being being loaded by the same class loader as the test2 was loaded by. We know it's getting a version of test2 because we're not getting a no class def found exception. We are getting the fact that it has a class, but potentially it's the wrong class. So what can we do? Well, we can grab test2, grab the class loader, and now we're going to call getResource, passing in the full package name and class name of our util2 class. This is the class we're trying to load. And we're going to replace dots for slashes, which will turn it from a package into a directory, and we're going to add .class on the end. So this will give us a path to the exact class which we have, which the class loader is loading. Okay, no assumption. This is absolute, truth from the class loader. So I'm going to hit save. I go back to my runtime and I refresh, and this is now the exact class which we are going to be grabbing from. I can see the directory is actually the same. We are in the same jar that we mentioned before, and we are grabbing that util2. If I wanted to really prove this, what I could do is I could extract util2. I always forget which way around this is. Util2 from CL demo. Is it that way? No, it's not. It's the other way. I'm going to extract from CL demo util2.class. There it is. Now, does anyone know how I can inspect the bytecode on this? Java P, exactly. So I'm going to type Java P util2, and Java P is a library which comes with Java itself, so the JDK, should I say. And so if I type Java P, all of a sudden we get this, basically default constructor, which is created for me by JavaOne, and there's no say hello method. If I wanted to be a little bit more interesting, I could, I think it's -c util2. Is it -c? Yes, it is -c. So if I type -c, then we actually see the bytecode. So here I can see in the constructor of util2, we're invoking something, a JVM instruction called invoke special. This is actually the invocation of a constructor, and then we're going to be returning the object which is created from that. So if you are interested in doing something like this, javapp -c is a very, very useful tool. But what I'm going to do is I'm going to also extract util3, and I want a javapp -c util3 as well. This is more interesting now. We can see not just the constructor, but we can see a say hello method. So we know say hello exists in util3. And all this is effectively doing is this is actually doing a load from a constant pool. The constant pool value it is loading is hello. This is effectively just like kind of almost pushing it onto a stack. And then the next thing we return, the next instruction is a return instruction. So we're returning what's on the stack. So we effectively pop hello off the stack and return that as part of our method. There's loads of really interesting material about Java bytecode, how you can manipulate it and how you can inspect it. So do check that out as well. Okay, so let me before I go into test 3, let me go back to here. I just want to go review what we just talked about. So in test 1, not enough classes. You can either get a couple of exceptions, class not found exception or no class def found error. The interesting ways that you can potentially look for this is mostly with something like this, a container specific log. You can also do this find star.jar -exec jar blah 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 and grep for my class. This is effectively searching the universe for your class. So if it is on your environment and you just don't know why it's not on the class path, you may want to do something like that. Also your IDE class lookup. This is really more going to be a build problem or a deploy problem. Stale classes, there could be a number of different exceptions which you might get, which don't actually look like class loading issues. They actually suggest, or some of them suggest, that there is a problem with your code. For example, abstract method error or class cast exception. These could be subtle changes that you've made that haven't been picked up, and as a result, you're seeing slightly different exceptions. Things like IncompatibleClassChangeError or no such method error. These are the kind of exceptions where you can see, where you can look at it and think there's a difference, but there's a clear difference between my code environment, my IDE, my source, and my runtime. Okay, now we're going to get to my favorite exception in Java. And if you don't have a favorite exception in Java, you should have. If you don't, maybe you could borrow mine. But my favorite exception, let's have a look at the test class. Okay, here we go. So what we're doing is we're in test 3. We call into util3. Oh, actually, no, what we're doing is we're Java developers, so we're going to obviously use a factory because we love factories. And we're going to have factory, and we're going to call instance untyped. If I click on that, we don't get some source. Let me find the source for factory 3. Factory 3, here's some source. So in our factory 3 source, what we're going to do, that wasn't to catch anyone out, that was actually just because I haven't linked that in Eclipse. In factory 3, we call instance untyped. What that's going to do is it creates a new instance of util3 and returns it just as an object, which is why it returns an instance of util3 untyped. So there's no type, it's just, well, there is a type, it's object though. So that seems fairly straightforward. We get back our util3, we cast it to util3, and then we call say hello on that. We know say hello exists because say hello is the bytecode. This is the bytecode we're going to run through. So I don't think we should see an exception here, except we get my favorite exception. Class cast exception. util3 cannot be cast to util3. Now, the first time I got this method, this exception, it was actually in the morning, and I'd already had a cup of coffee. I had another cup of coffee, and that didn't take it away. I had another cup of coffee, that didn't take it away. And I'm starting to question myself here, starting to question the output from the JVM, certainly. Who else has seen this kind of exception? 1, 2, 3. Quite a few people. Okay, and this shows a couple of things. This shows how problematic class-loader class-loader bugs can be, and also how crap output and debug information is. That this actually gives us no information as to whether it's a class-loading problem or not. Of those people who did find this exception, who actually fixed it? There are always fewer hands, actually. I bet everyone else just decided to work on a different problem and left it for someone else. Probably that's almost certainly what happened. Okay, so for everyone who didn't put their hand up, what's happening here? Why am I getting this? This is the hardest question I'll ask.
There are different, the same class name exists in different packages. Two different packages.
Two different packages, I heard. No, the packages are exactly the same. The bytecode is exactly the same for util3.
And the next suggestion was that the classes come from different class loaders.
And they're actually different.
So this is the key thing. Let's talk about a class, the identity of a class, just for a second. A JVM considers 3 parts to a class which denotes its identity. You have the package of the class, you have the class name itself, and the third thing is the ID of the class loader that created that class. If each of those 3 items are not identical between 2 classes, the class will not be recognized as the same class in the JVM. So just to reiterate, if I had exactly the same class name, exactly the same package name, in fact, exactly the same bytecode in the class, just because it has a different class loader which is loading this class, the class loader will not respect that it is the same class. So for example, in this case, what we have, util3 cannot be cast to util3. This is exactly true, because util3, even though it has the same package name, the same class name, the 2 instances of util3 could potentially have a different class loader. And of course, as I've been talking previously, we don't want to assume anything. Let's actually work out why this is the case. So let's go to our test through. I'm going to comment this out. I'm going to comment that out, and I'm going to uncomment this. And let's diagnose. Let's understand where our assumptions are coming from. So we have 2 places that are referencing util3. We have this part here, which is test3. So what we're going to do is we're going to go test3, get the class loader name, get the resource. So where is test3 accessing util3? Pass in the full name of util3, and let's turn this into a path. The next place we access util3 is in our factory. In our factory, this is where we actually create util3. So we go to factory3, grab the class loader that loads factory3. Because they're in different scopes, there is the potential for a different class loader. And then we do all the same stuff, util3, get the full name of util3, including package name, and turn that into a path for us. So I'm going to save that, and I'm going to rerun test3. Lo and behold, we get 2 different locations. One location, this is where test3 is getting its class. So test3, where we're trying to perform the cast, is using the definition in this, is using exactly this bytecode to try and cast this object to. However, the class which we're actually creating is found here. And if I was to cd into this location, here we have a cldemo.jar, and I can do exactly the same thing. In fact, I'm going to jar that -c util3, and it's exactly the same bytecode. So this is an identical class, but just being available in 2 different places in the runtime, and is being picked up by two different class loaders. So let me show you how this is possible. Go full screen here. So how is this possible? This is what we have. We have this code right here, util3u equals factory.3.instance untyped casted to a factory3. This is the code we're running. The first thing that we're actually going to do is try and grab. Let's say we're going to grab factory3 first. Factory3, we need to instantiate factory3. So what we do is we're in Tomcat. We're running in Tomcat, and Tomcat has a local first strategy when dealing with loading classes from a class loader. So we start off here in the web class loader. Now the web class loader on its class path only has util3 and test3 on its class path. We're looking for factory3. We don't have it. So the web class loader has failed in trying to load factory3. So only then will it propagate up to the next class loader. That happens to be the shared class loader. The shared class loader does a search or does a lookup on its class path trying to find factory3. We have got factory3 here, as you can see on the class path. So this is essentially on the class path in a jar in our shared directory on Tomcat. So we load an instance of factory3 there. Now we have our instance of factory3. What we're going to do is we're going to make an invocation to instance untyped, which is up here. Instance untyped performs a new util3. It constructs a new instance of util3. As a result of this, it needs to load util3. Now, the shared class loader is the scope in which factory3 was created, and we are in factory3 when we create util3. So we go to our shared class loader first because that's the class loader that created factory3. As a result, the shared class loader has util3 on its class path. So it tries to load locally first. It loads util3 from the shared class loader. As a result, the identity of util3 is now its package, its name, and the shared class loader ID. We return this as an object down back to our test3 class, and this is when test3 goes, right, I need to cast this object to an instance of util3, but the web class loader has never seen util3, so it tries to load that first. So it goes to the web class loader and it says, can you please load me an instance of a definition of util3? And rather than go parent first, its strategy is local first. And locally, it does have an instance of util3. So it loads that instance of util3. If at this point we had gone up to the shared class loader, the shared class loader has already loaded util3, and the shared class loader would just pass that instance of class back to the web class loader and say, sure, use this one. And we would have a common util3 class that we could cast, and there would be no problem. However, this util3 has the identity of the util3 class name, the same package, and an ID of web class loader, which conflicts with the ID of shared class loader. And that's why we get a class castle exception here, because the two util2s from the JVM look like two different classes. In fact, they are so different, it might as well be different bytecode, different class name, different package name, and so forth. Any questions on that?
Yeah, go ahead, Jason.
The factory3 class, was that in the shared class loader because it was in Tomcat's lib directory?
Let's have a look. So if I was to go into, so where are we now? We are in the lib directory. No, we're not. Let me go to So here's the shared directory. So let's go into here, cd that. Here's a shared jar. This is the shared jar which it was saying here, shared jar. So if if I jar minus tvf in that shared jar, we'll get a number of things. First of all, we get util3 where that was found, but most importantly, we'll get factory3 as well. Oh, sorry, the other way around. We'll get factory3 where we invoke that, but most importantly, here's the util3 class, which factory3's class loader finds. Does that answer the question?
Yeah, thank you.
Okay. Any other questions?
Are your files dated 2013?
Are they? Are they really? Oh, 2013. Yeah, that's pretty old, isn't it? I have no idea, actually. I guess, in fact, this is actually a fairly new laptop as well, so who knows?
It's just time zone differences here.
Yeah, exactly right, yeah. You guys are in what, 2018 now, right? Okay, so there are different types of problems we can get. Let's go to test 4. Test 4 is going to be subtly different in that this time we're going to call factory3.instance. Okay, if we was to go into instance, what we're actually doing on instance here is we're returning an instance of util3. So what does that eliminate? Well, that eliminates the need to cast. Okay, so if I was to save that and actually run test 4, because we don't need a cast, surely there won't be a problem. Well, yes, there is, but we get a slightly different error. We get a linkage error. And in this case, we do get a little bit more interesting information because we're actually talking about class loaders. You know, it's a shame we don't get this kind of information on the first version because that's often more common. But this gives us a little bit more interesting feedback. Another example, and this is a really interesting example. This was one that I have had before, but is one that took me even longer to work out. Here we have instance package. We do exactly the same as we did in test 3, except there is a very subtle difference between instance package and instance untyped. Can anyone see what that difference is? It is exactly right. So this is a protected method. This is almost like a private equivalent package scope. So effectively, we have to be in the same package to invoke this. So what do we get this time? This time we get an illegal access error, and to me this says, okay, there's a problem in my code. And to me, I would continually redeploy, changing the access modifier on my method. And this took me a number of times before I even realized it was a potential problem with my class loader. This is a very, very hard one to understand that it's your class loader, because you typically have to go straight into your bytecode to even realize that the class that you are seeing is actually the class that you expect. There's a problem there. So don't necessarily think just because it isn't a class loader exception that it's not a class loader problem. Okay, so let's do a quick overview of some of those bits and bobs. Full screen this. Okay, so more class loaders than classes. So if we have multiple class loaders, we can get linkage errors, class cast exceptions, illegal access errors. To troubleshoot, the best thing to do is get resource on a class loader, but try and work out which class loaders, why you're getting multiple class loaders. You can also do minus verbose class on your JVM startup, but this is actually very verbose. If you have a very specific problem, it might be easier just to do class loader.getResource and add debug. Okay, any questions on that before we talk about class loader leaks?
Yeah, is there any reason those other exceptions don't give that class loader information?
There has actually been, I think it's a JEP or some bug in the OpenJDK since, I think, and this maybe make you laugh, it's I think 2005. But it's just something which was never really acted upon for whatever unknown reason. It is very frustrating, and it's not like it's an occurrence which is so rare that people will never see it. I mean, even in this room, we had 5, 6, 7 people who put their hands up. So it's extremely frustrating that it's not. But I don't see any reason why it hasn't been there. I can only apologize. Okay, So let's talk about class loader leaks. Class loaders have a link to every class they create. We already discussed that classes have a link to every class loader, to the class loader that created it. But the key part is every class loader has a link to all the classes it created. Now, what this means is it effectively has a lot of memory, right? Because it has to hold all the static fields in every single class it creates. If you leak a single class, well, you essentially just leak that class. But if you leak a class loader, then what you're actually leaking is a class loader and every single class it creates. If you're actually trying to destroy part of a class loader hierarchy, for example, like you want to do a redeploy, by leaking a class loader, you leak classes and static fields, which can actually link over to existing instance variables, or instances of objects. In which case, you could actually not just leak a class loader and a class, but also a bunch of objects as well, and all the objects they link to. So leaking a class loader can be very, very dangerous. But what does it actually mean? How can we leak a class loader? We barely use them. Explicitly, that is to say. Well, every time we do a redeploy, for example, which is updating our application in our runtime, this is what we effectively do. And the reason we do this is because a class loader is very well named. It loads classes. It doesn't unload class. It doesn't reload a class. What we're effectively doing is saying, I'm going to create a new class loader, or a set of new class loaders for my application. I'm going to reload, or load, should I say, classes from scratch. I'm going to then try and recreate all my objects and potentially carry state across. And this is the problem area right here. This is the problem area where we recreate the object and we pass state across. If there is a problem in passing the state across, we're going to get a potential, a little bit of hangover there. And if we do leak this single object when we're trying to pass that state across, we're not just leaking the object, we're leaking the class, and we're then leaking the class loader, because we can't destroy this because of this reference. And there are a number of reasons why these references can exist, from recovery of data source providers and things like that, all the way through to just bad implementations on vendor sites. So if we leak these kind of references, we're leaking the class loaders and all of the class loaders they reference, all of the classes they reference, and potentially objects they reference in their static fields as well. So let me show you how this happens. I'm going to give you a quick demo. Let me get rid of all these. I'm going to give you a quick demo of, here we go, ZT server. This is a very plain server which we created. Let me just show you some of the code. And what this server is going to do is, it's in a while loop, while true, so infinite loop. And all we're doing is we want to create a web app. And every single time we come through this while loop, we're going to create a new instance of my web app using this web app factory. What we're going to do is we're going to print out a message which gives us some text and also gives us a number which we increment on every iteration of this loop. We're also going to do a thread sleep, so we're going to make sure we go through this loop every minute. Let's have a look at the actual web app itself. Actually, no, let's go to the web app factory first. So in the web app factory, let's go to the code that actually does something. In the web app factory, every single time we go through this loop, what we're going to do is we're going to create a new class loader. And in this class loader, we're going to, this class loader has a cache as well, which is a new long with it's effectively quite a large array. This is actually a visualization, as it were, or a placeholder for the kind of static data which a class loader might carry. So consider this array as a bunch of static classes, a bunch of static fields, potentially links to existing instances of objects through its static fields. Now, what this is doing is it returns our web app every single time. Nothing really too exceptional in this code. All it's going to do is pass us a new instance of a web app, but it's doing it with a new class loader every time. As a result, I could potentially make changes to my web app class and see those changes live in my runtime. And I can do this because we're creating it we're loading it every single time from scratch. So as I compile my class, and that goes to my file system, my new class loader is going to be loading the new instance of that class and creating an object from that new instance. So my string message is going to be version 1, and we're also going to have a counter, which is going to be called where is it? There it is, a static counter right there. So let's execute this. So I'm going to kick off this without JRebel. And where's my console? Here's my console. Right, so we've kicked it off. We have every second we get a new message popping up here. We have version 1 equals 0. So let's make a change. If I wanted to, because our class loader is being created from scratch for every single time we go through this loop, I could change this to version 2. And as I hit save, you'll notice version 2 all of a sudden appears. So I'm effectively live coding in my runtime because we're creating a new class loader every time we go through this loop. So we're picking up the new class every time we go through this loop. The one problem is, of course, though, that as every time we go through this loop, our state is being lost, because every time we go through this loop, we're effectively throwing away our old class loader, our old class, and where we increment our counter, that's not being passed across. So let me stop this and come back. We can change that quite easily by coming in here. And what I'm going to do is I'm going to add on my my web app interface, I'm going to create a method called copy, which takes in a web app. I'll save that. And on my web app, I'm going to uncomment this. This is a great new development methodology called development via uncommenting. It's a very bug-proof way of developing. And what I'm going to do is I've implemented this copy method. And every single time we go through this loop, copy is going to be called. And what I'm doing is I'm checking if this is not null. If it isn't null, we take the counter from what we're being passed and set our own counter to it. So we're pulling state across. So I save that, and the only thing I need to do is actually invoke this. So I'll invoke it with copy of web app. There we go, already done for us. So every time we're going through this now, before we create a new instance, we're passing our web app into it. We're grabbing just an integer value from that. So there's no reference at all. We grab the int value, and we store that in our setting. So if I was to rerun this now, what we're going to do is each one of these is now a new class loader loading a new class and keeping state from our previous instance. If I wanted to, I could even go in and I could go to my web app. I could still change my version, change it back to 1, and you'll see our version number changes, showing they're different classes. They're loaded by different class loaders, and we're still maintaining state. Now, this is all very well and good, but there is a problem, and that problem is that this is actually very hard to do when we actually do this on a bigger scale, and we will introduce leaks. So let's introduce a leak. I'm not going to sugarcoat this in any way. We're going to call it an iLeak. I'm going to create an implementation of iLeak. There we go. And all we're doing is we're creating a new class called leak. We return that, and crucially, we're in our copy method, we're holding a reference to that leak object. So now, when we go through this loop and we create our new class loader, which creates our class, we try and pull state in from our previous object. But when we do so, we maintain a link to our previous object. As a result, we leak that class, we leak the class loader, and crucially, what we're going to leak is, where is it? Yeah, yeah. What we're going to crucially leak is that we're going to leak this URL class loader and all of this, potential memory drain here every single time the class loader is created. So let's run this now. Everything's saved. Let's run that again. Okay, so here we go. We're still running. I can still show you that in my web app. I can change this to version 2. Oops. If I have time. I don't think I'm going to have time. Do I have time? Just. And now, bang. Okay, I've given this session enough time to know exactly which one it dies on. So I just in time changed it to version 2 to show you that these are different classes and different class loaders. But this time, because we had a problem in our transition where we were trying to destroy all our previous class loaders, we couldn't garbage collect them because of a reference being hung over. As we're amazingly good Java developers, in our run configuration, in our arguments, we have a heap dump on out of memory error. And this is something which you can use in production so that if you have an out of memory error, you can still have some understanding of what happened before your JVM went down. As a result, we have an hprof file, which is a file which we can read in using something called MAT, which is a memory analyzing tool in Eclipse. If I just refresh this, let's refresh there. Whoa, there's our hprof file. I can open this file up. I'm not sure if you'll be able to see this that well, actually. Hopefully you will. Okay, so what I'm going to click on here is something called Dominator Tree. And here, this is actually what our heap looked like the seconds before it died. And I can see, I'm going to look down this column right here, retained heap. And I can see the huge number there. So the first thing I can see is my heap is way too big for Eclipse, and I need to sort that out. But if I scroll down here, and I'm just opening up the twisties, I can see that every single time I'm going through here, what we're doing is we're leaking 160 meg. I can go into one of these, and I can see exactly where the leak occurred. And here it is. The leak is occurring at 160 meg, or 160 meg is being taken up by this long. So we can see exactly where our problem is, and it's effectively our class loader. This is the representation of a class loader with lots of additional classes, static content, and potentially instances of objects as well there. So that's how class loaders leak. The one thing I wanted to show you as well is how a tool which we create does something similar. Not leak, that is, but reload classes. Now, who's heard of a tool called JRebel before? Okay, a good number. So one of the things that JRebel does is JRebel performs a instant update of your code during runtime. But it doesn't do this by destroying class loaders and creating class loaders. Instead, what we do is we manipulate bytecode in the runtime so that your new code that you write in your IDE is represented in your existing objects in your code. So we're not expecting the class loader to reload any classes. What we're expecting it to do is load minor versions of that class, and we write some code which redirects you to the latest version. So let me show you exactly what I mean. So let me go full screen here and go forward. So when you're using JRebel, which is a tool you can install in your JVMs, when you try and load an application class like this one here, class A, let's take a look at class A. It has 3 fields and it has 3 methods. What we actually do is, using a JRebel transformer, we actually add code into an existing Java class loader that, rather than load class A as is, will actually load a couple of versions of classes. First of all, it loads class A. So we load with the same name. It has state, so we load a number of fields, and it also loads with proxy methods. So this is almost considered like a dynamic proxy. We also load a version of class A, which contains behavior. So we denote its version by a number here, so it's class A0, and we have a number of methods but no state. The methods are simply its behavior. Let me give you an example of how this would work. So here we have a class C, it extends a class X, and we have a little bit of state and a couple of methods, a bit of behavior. So we have some structure of the class, some state, and some behavior. What a JRebel enabled runtime would do when it loads this is it would first load a class C, which extends X. Notice that the signature of the class is the same. We still have the state where the signature is the same, and the methods where the signatures are the same. But the one difference is our behavior. Our behavior in our classes is very, very different. Rather than actually just run this behavior, the X plus Y, and return that manually, what we're in fact doing is we're redirecting the behavior to another class, which is going to actually run that for us. And that class is going to be, in this case, C0. So this is C0. It doesn't contain any state, so it's an abstract class. As a result, we have static methods, and we have one additional input parameter, which is C. And C is the instance of this original class which we created, and we pass ourselves on the redirect to this minor version of the class C0. So what we do, this is where we actually run our behavior. If we want to grab instance variables, we get it from the class C. Here's another method too. If we want to actually invoke any other methods, such as in this case system out, we do that via a redirector as well. Now, what this provides, this is just the mechanism which JRebel uses to perform reloads. How does it now perform a reload? Well, if you was to change your instance of C in your IDE, and in this case what we're doing is we've added a method Z or Z, and we're updated method 1 to use that method Z. This is the change that we're making in our IDE. Of course, in our IDE, we don't see any of the C0, any of these method changes or class changes. This is what we see. This is our code. Now, to make this update, what JRebel does under the covers is it creates a new version, a C1 version. In fact, this should actually be abstract as well. And in this C1 version, we create a new static method, which is C. C doesn't have, which is Z. Z doesn't have any parameters here, but we will of course have a C parameter again. And this returns a value, just returns 10. There's no code behind it. We also update our method 1, so we still have method 1, and all this does is it grabs the version, it calls into Z and returns the value that we get from that. The key part here is in our redirect code, in our transformer code. When existing classes try to access C, they don't know which version of C their behavior is going to come from. All they know is they're effectively going through this dynamic proxy, and that dynamic proxy will take us to the most recent version of C, the behavior of C. So effectively, what actually happens is, rather than have a completely new hierarchy of class loaders and classes and objects, when an object gets changed, when a class gets changed, the JRebel agent actually pushes that code directly in to existing classes and creates a couple of behavioral versions. But your existing class loader and your existing objects remain, and state is the same. There's no kind of state transfer between any of these. And I think that's pretty much everything I had to say on JRebel, unless there are any questions on JRebel. Actually, I have a couple of other things I could mention, which is how we injected JRebel into, let's talk about this. This is how we actually injected JRebel into the JVM. Basically, we whenever you want to hack a class loader or manipulate Java bytecode, you need to effectively give yourself a hook. And the hook which we use here is an agent hook. This is a Java agent. And a Java agent is very simple. All it is a jar which contains a class, and we have a manifest in this jar. And this manifest has a pre-main class, and it points you to where a class exists which has a pre-main method. And at this point, we can call this instrumentation method called add transformer and provide our own transformer if we wanted to. This is a class file transformer. This gives us a hook to actually manipulate the bytecode when the class loader tries to load its class. The last thing actually we need to do is when our JVM runs, we need to add this JVM property, which this minus Java agent : and then a path to our Java agent. This points us to the jar which contains this agent class as well as this manifest file. What then happens is, and I think this is using Java Assist. What then happens is our class file transformer, which we registered just previously, when a class gets loaded, we'll be provided with the byte array of the class, and as a result, we can do whatever we want to this class. I can, for instance, call my own method which transforms a class and transforms this. Hang on, where are we? Here. This is the byte array which we're turning into a byte array input stream. Don't worry about this part too much. The class pool. This is effectively just how Java Assist grabs its class path and some things. But the only thing we need to care about here is that before a class gets loaded, we can grab the bytecode and we can manipulate it. And in this method here, transform class, this is just my method that I've created. In this class, we can use ASM or ByteBuddy or whatever we choose to manipulate our bytecode. And things like this is typically done for profilers to add start and end times to existing methods, or as we're doing to manipulate the bytecode that's loaded in order to make changes to them live during runtime. Okay, so let me jump back to class loader slides. I think that's pretty much about me done now. So what I'll do is I'll full screen this. And I'll say, okay, first thing to do when we're looking at class loader problems is validate your assumptions. It's very easy to assume your class loader is doing one thing, but in your runtime, you're actually doing something very, very different. Leaking class loaders is very easy to do. And it's also one thing I'll add to this is that it's not just easy to do, but it can be quite disastrous when it happens. Previous to Java 8, we of course had, I think it was Java 8, yeah. Previous to Java 8, of course, we had the permgen space. And this is the space in which all classes, when they were created, this is the space they existed on the heap. And this was always a smaller piece of the heap. And Java didn't expect this to change because Java classes are immutable. You can't change them. As a result, when you did try and do a number of redeploys and you leaked class loaders and classes and all kinds of things, the permgen space will be filled up very, very quickly. And I'm sure many of you who used Tomcat and tried to do multiple redeploys would have seen a permgen out of memory error after maybe 5th, 6th, 7th time of doing a redeploy. This is exactly what's happening. It was a class loader leak which led to your JVM going down. Isolation would work here for your processes, but it's something that really won't happen that soon, I don't think. There is a JSR for it, but it hasn't been touched for a long time. And JRebel obviously rocks, and everyone should go and buy it. And yeah, that's pretty much everything I had for the session. So we've got a few minutes left. If happy to take questions if anyone's got any final questions.
How does it work? You have multiple Java units. How does JRebel interoperate with something like New Relic or another Java agent?
Could you? Sorry, I couldn't hear that question.
So the question, just to repeat, was how does JRebel's Java agent interop with other Java agents, like say New Relic?
Yeah, great question. So Java agents are notorious for not interoperating with each other very well. Typically, the only times that Java agents will work well together is when they come from the same vendor. And that's because it takes a huge amount of effort and work to make sure Java agents run together. For example, if I were to grab some bytecode from a class, that class may have potentially been transformed previously by someone else. I may want to transform that class myself on top of what another Java agent has done. So very often they won't work out the box if you use multiple. Very often it depends on the order of which you specify the Java agent or which you attach the Java agent to the JVM. But typically it does need to be developed together in partnership. It really depends on the type of change that the Java agent is making. But for example, we have another product called JRebel. In fact, I think that may have been. If I go back to my, where is it? That's weird. Oh, I know. It's probably just. There we go. This is actually another Java agent itself. So, for example, if I was to come here and I'd say, here's my pet clinic application, I've got JRebel running here, and I've got JRebel running as well. So, what I could potentially do is I could say, well, let's update this welcome message. I can go to my messages.properties file. I can say welcome to Melbjug or something like that. There we go. Let's make that save, and I can run this, and we get that updated in my runtime here, and we still have JRebel running here. And in fact, I can actually have a look. This is actually a profiler. I can actually see what's happening in my application under the covers. See where my time is being spent, see if there are any IO calls to databases and that kind of thing. And they're running together, but that's because they've been developed together. Does that answer the question?
Yeah, thanks.
Cool. Any other questions?
I've got a dumb question, Simon. When does the actual class loading happen? And is it possible that you can have threads having different class loaders? How do threads share a class loader, and could you get into any mischief with that?
So class loading tends to happen when you it's done lazily, effectively. So it very often happens when you access when the thread needs to load that class. There are other times where it will see if a class exists. That's one of the reasons why you have different exceptions. But Java works on this quite lazily. In terms of sharing class loaders, yes, you can put you can pass class loaders around, and a lot of people do try that when they do get in trouble with some of these environments by passing class loaders around, trying to load a class and using those classes specifically loaded by certain class loaders to move forward. It's one thing I did when I was at IBM. I helped implement some of the OSGi containers in WebSphere, and if you think class loaders are quite complex, then take a look at OSGi class loaders, because essentially, rather than having a flat class loader, what you would have is a class loader for every bundle, because rather than just have one flat class loader that everyone adheres to, you have class paths which are defined by imports and exports and so forth on bundles. So every class loader every bundle has almost like a different scope and so forth. So in many of the cases during that development, you do pass around class loaders to purely as a middleware developer. We would pass around class loaders to make sure the right things are loading the right classes. It's not common. You would need a reason to do it, but it is done.
Cool. Thanks. Any other questions?
Just curious about the trends of the when you see these issues, like Java EE is maybe dwindling a bit, and OSGi is a bit specialist. Are there other cases where you see these issues happening?
So I think OSGi has its kind of OSGi is quite specific. You're right. It does fix the problem of this jar hell in that because you don't just have a clear hierarchy whereby you might have different classes in different places. With OSGi, you can link directly to a specific version of a specific library, and as a result, you do avoid some of those problems. But it is specialist, and it's not necessarily the reason one might choose OSGi. You would choose it because you wanted more modular code and things like that. Java EE, while Java EE may be slipping slightly in terms of Java EE is a weird phrase actually, because a lot of people who say they're using Java EE are actually just using servlets. A lot of people who say they're using Java EE are using a proper hardcore Java EE, EJBs and all sorts. So if we take something like Spring, for example, even Spring builds on top of a lot of the Java EE specifications. And as a result, we will still need containers that have some level of support from Java EE. Basically, if you're not in OSGi and you're not using or something like that, and you do have this kind of hierarchical class loader structure, you will see these kind of problems. And Spring is a classic example where I'm sure plenty of people have seen these kind of problems in Spring just by deploying at your application some parts in the shared class loader, some parts in your application class loader. Basically, if you can do it as high as possible, that is the ultimate, whereby you effectively load fewer classes in the runtime, so your code will be more performant anyway, but you have a lot less chance of this conflict with class loaders. So there's not necessarily one specific area which will see this problem. If you're using pure Java SE without kind of containers and stuff like that, it's going to be you'll be there's a lot fewer rarer chance of you seeing these kind of problems. But really, if you're using a container, it's open season for these problems.
Thanks.
Okay, no worries. Thanks.
All right. Sorry, a bit of echo. Let's try and stand over here. Try and stand. No, okay. All right, cool. Thank you very much, Simon. Really appreciate you taking your morning out. Big round of applause.
Thank you.